no introduction. Adithya Devraj was a grad student working with me until last year, and absolutely a star. He was just really an inspiration when he came to started working with me. And by the way, at University of Illinois, for 15 years, I asked students in my stochastic control course to look into variance of Q-learning. None of them took the bait except for Adithya. And that's what actually launched this whole ZAP thing. Yeah, he's a University of Florida Informatics Institute fellow, which gave him some of his funding. He got me some of my favorite gigs in terms of lectures and funding when he was a grad student, because he was more in demand than me when he was a grad student as a speaker and so forth. And now he's a postdoc with Ben Van Roy at Stanford, where he's learning all sorts of new stuff in information theory and RL. So, Adithya?
Thanks, Sean. Thanks for the wonderful introduction. And also thanks to Emma, Mengdi, and you for giving me an opportunity to speak here. And also all the other organizers for organizing this wonderful workshop. So today I'll be talking about my work on Q-learning with uniformly bounded variance. And this is based on joint work with my wonderful collaborators like Shuhang, whose work you just heard about from Sean, and also my advisor Sean Mine, and Anna Busichat Andrea. And thanks to all the funding agencies for sponsoring my research, and Aero, NSF, and UFII, and also the Simons Institute for organizing these sort of workshops. And I was like beneficiary of this thing back in 2018, where I enjoyed a lot, like of my 5 months of my PhD. So okay, let me just begin. So the motivation for this talk is this sort of a finite and bound that seems to be like very popular in a lot of recent theoretical reinforcement learning papers. So here, theta star is some sort of an optimal parameter vector that parameterizes your either Q function or your value function. And theta n is an estimate of this theta star after n iterations of running an algorithm. Gamma is a discount factor, so that's a different notation from Sean's talk. So gamma denotes a discount factor instead of beta, and B is some scalar that depends on the dimension of the state space, action space, or the number of states, actions, etc., which we don't really care about. And as I said, n is a number of iterations. So what I'm really interested in here is this this factor here, this 1/1 minus gamma to the p, that seems to blow up as the discount factor gamma goes closer to 1. And what we really want to try to understand is this factor necessary in this finite time bounds, or is it possible to sort of avoid it? And here are a few examples where such a bound appears in many papers. And most recently, we saw such bounds appear in both Martin Wainwright's talk and also in Rahul Jain's talk. And the spoiler alert is that this sort of a factor is essentially due to estimating a constant in this value function or the Q value function. And ultimately, this may not be something that you care about. And in many cases, we think that this can be avoidable. And I'll show you how to do that. Okay. So here's a basic overview of the talk. I'll keep this discussion on stochastic approximation short since Sean just covered it, but the rest of it is just on convergence rate analysis of Q-learning and relative Q-learning algorithm, which I'll be introducing shortly. So first, the problem setup will denote X to be the stationary controlled Markov chain that's evolving on a finite state space X, and also this boldface U to be the input sequence or the action sequence, and that's also taking values on a finite action space. We'll denote this PU to be the transition probability matrix. That is, given current action is U and the current state is X, the probability of transiting to state X prime is given by this over here. And we'll denote C to be the cost function. Okay, and also the gamma to be the discount factor. So given a policy, feedback policy phi, we'll denote q phi to be the q value function that corresponds to policy phi, and that is given by this infinite summation over here. And this optimal q function q star is the minimum or all policies phi of q phi. Okay. And it is well known that this optimal q function q star solves a fixed point equation known as a Bellman equation. So here T denotes the Bellman operator that is defined over here. And we'll also use Q lower bar to denote the minimum or all actions of Q star. Okay, so that's just some notation setup. The goal in dynamic programming is to find the solution Q star to this fixed point equation Q star equal to TQ star. Okay. And one way to interpret this dynamic programming goal is the following. Let's say you have an input sequence UN that makes sure that you visit each and every state action pair X and U like infinitely often. Then solving this conditional expectation equal to 0 for each and every N is equivalent to solving this fixed point equation. Why am I writing it out like this? So this is the reason. So the goal in Q-learning can be interpreted as sort of an approximation to the dynamic programming goal. So let's say you're given a parameterized family of Q functions Q theta. So here theta denotes the parameter vector. It's taking values in RD. The goal is to find one interpretation of the goal is to solve this what is known as a projected Bellman equation, where you're taking this term inside this conditional expectation. You're removing the conditioning, and then you're hitting it by a d-dimensional sequence known as the eligibility vector, which I'm denoting here by zeta n. Okay. And usually the parameterization and this choice of zeta n is part of algorithm design. And one very popular choice of for this eligibility vector is just choosing it to be the gradient of the Q function, which, as Sean already mentioned, is what essentially is done in DQN. Watkins Q-learning, or as is well known as tabular Q-learning, is a very special case of solving this projected Bellman equation. So in this setting, the parameterized family is Q theta is linearly parameterized with basis function denoted to be psi. The eligibility vector zeta n is essentially equal to gradient of Q theta, which is equal to the basis function itself. The number of basis functions is actually equal to the number of state action pairs, and the basis functions are chosen to be the indicator functions. So this is called the complete basis setting or full basis setting. It's well known that solving this is equivalent to finding the exact Q function. And why is that? So if you choose this set of hyperparameters, the linear parameterization and also complete basis, then this f bar of theta star that is written over here can be written in this form. So here pi is a diagonal matrix with each of its component being the stationary distribution of this Markov chain xu. Again, q theta star is the parameterized Q function that corresponds to the optimal parameter vector theta star, and T is the Bellman operator. Okay. So if you look at, let's say you solve f bar theta star equal to 0, clearly if your exploration policy is chosen in such a way that the stationary distribution of xu is non-zero for each and every x and u, then solving this f bar of theta star is equal to 0 is equivalent to solving this Bellman equation. Okay, so that should be clear from looking at this equation here, and that's the reason the tabular Q-learning algorithm is known to solve for the exact Q function. So I want to make a remark here. So I know that not many people are interested in tabular Q-learning algorithm, but the point here is to use it as a sort of a vehicle to introduce the concepts that I'll be talking about, essentially, like in the tabular Q-learning case, like things can be made super precise, but the ideas that I'll be talking about can easily be extended to even function approximation Q-learning or function approximation TD learning or whatever. So I guess that will be clear shortly. But I just want to remark that tabular Q-learning is not really the goal of our work here. Okay. So in the relative Q-learning algorithm, the goal is to solve a modified fixed point equation. So here T tilde, let's call it the relative Bellman operator. So it's the same as the Bellman operator, except that you're also subtracting of a constant here. Okay, so this is part, so T H star would be just these first two terms, and T tilde H star is the first two terms minus some constant. Okay. So here, this constant here, it has like two hyperparameters, delta and mu. So delta can be like any positive scalar. I'll get to like how to choose it much later on. And mu is some is a PMF. Okay, and mu H star is basically the expectation of H star with respect to this PMF. Okay, and the choice of mu really doesn't matter for the results that I'll be talking about. Okay, let's say you solve this modified fixed point equation, H star equal to T tilde H star. So can we get Q star back from H star? Yes, it's pretty easy. Like it's just offset by a constant here. Okay, so and that depends on delta and mu. But the real question here is, do we really need Q star? So ultimately, why do we estimate the Q value function? Is we estimate it so that like we can apply a greedy policy and get the optimal policy. But if you look at this equation here, the optimizer of Q star is the same as optimizer for H star, since the constant doesn't really matter. So estimating H star must essentially be sufficient for you to get the optimal policy. And this sort of analogy is true for even when you apply, TD learning algorithm as a part of, say, actor critic or even LSPI kind of algorithms, wherein the ultimate, the use of this estimating the value function is to get the next policy, and that you can get even if you don't estimate the constant correctly. So. And again, I'll be highlighting that again, but I guess my point here is you don't need the constants to, in many cases. And in fact, like I think there are I'm not sure where exactly you need the constants are really important, but I guess I'll leave the discussion to later on. The bigger question here is, okay, let's say you estimate this H star. Is there any advantage of estimating H star instead of Q star? Is there any advantage of ignoring this constant? And to explain this, I need to get into a little bit of stochastic approximation. I'll be quick since Sean already covered this. But I'll highlight the things that are actually necessary for the results that I'll be talking about in this talk. Again, this slide I'll be like super quick since, again, Sean just covered it. The goal in stochastic approximation is to find theta star, so that f bar of theta star equal to 0, and f bar is actually an expectation. The algorithm dates back to Robinson and Bunro in 1951, and it's given by this recursion over here. So here I'll be assuming that the step size alpha n is like a scalar gain step size. So alpha n is like g over n plus 1. In the next slide, I'll be making a comment about that because you just saw Sean's talk and you'll be like, why would anybody do a scalar step size stochastic approximation? But I'll make a comment about that in the next slide. And the way you analyze this discrete time recursion is by looking at this deterministic ODE, and that actually is like is foundational to proving stability and convergence analysis of convergence of the stochastic approximation algorithm. And one way to view this stochastic approximation recursion is to view it as a noisy Euler discretization of this deterministic ODE. Okay, and for the tabular Q-learning algorithm that is like currently of interest over in this talk, this noise is essentially a martingale difference sequence. Okay. Now, what we are really interested in this talk is like the convergence rate of stochastic approximation algorithm. Okay, so let's denote theta tilde n to be the error sequence. So how far away are we from theta star after n iterations? The performance criteria here is going to be the asymptotic covariance, which is given by this limit over here. Okay, so clearly, if this asymptotic covariance is finite, then that implies a 1 over n convergence rate of asymptotic convergence rate of the mean square error. What the asymptotic variance theory for stochastic approximation says is the following. Let's denote sigma delta to be the noise covariance matrix. So again, delta n is a noise sequence that appears in a stochastic approximation algorithm. And A is the linearization matrix of this. So it's a linearization of f bar at theta star. What the asymptotic variance theory says is that if you choose a stepsize sequence G over n plus 1 in such a way that all the eigenvalues of this matrix GA are strictly smaller than minus half, then the asymptotic covariance is finite, and it can be obtained as a solution to this Lyapunov equation over here. Okay. And if there exists at least one eigenvalue of this matrix GA that is bigger than or equal to minus half, then the asymptotic covariance is typically infinite. And again, therefore, the convergence rate is typically slower than 1 over n, which is the best convergence rate. Okay. And all the asymptotically optimal stochastic approximation algorithms, they achieve asymptotic covariance they have asymptotic covariance of A inverse sigma delta A inverse transpose. And some of the examples here are the LSTD lambda algorithm, Rupert's stochastic Newton-Raphson, all this averaging techniques, ZapQ learning, momentum, etc. And this is a picture of Rupert, I think, who is responsible for at least two of the algorithms here. So yeah. So the comment I want to make about this constant step size algorithm is this. So the idea, the theme is going to, in this talk is going to be that we're going to compare the best scalar step size Q-learning algorithm with the best scalar step size relative Q-learning algorithm. I think it will be clear when I show the results that the performance difference between these two algorithms carries over when you apply, say, for example, averaging or ZAP to Q-learning and relative Q-learning. And that's because essentially, again, as kind of spoiler alert, we'll be changing the A matrix. Because we're changing the problem, we are going to make the linearization matrix a better condition. And again, that should be very clear. But again, the point here is, sure, you may not be interested in scalar gain algorithms, but even if you apply Rupert-Pollack averaging to both Q-learning and relative Q-learning algorithms, you will still observe this performance difference that we want to show. Okay. Now that we have, okay, I have 10 more minutes. So now that we have covered the stochastic approximation, convergence rate of stochastic approximation, let's apply it to Q-learning. So firstly, Q-learning is stochastic approximation. It is given by this recursion over here. So if you let's start with a stupid step size alpha n is like 1 over n. In this case, the linearization matrix A can be written in this form over here. So P phi star is the transition matrix that corresponds to the optimal policy phi star. And you can show that the maximum eigenvalue of this matrix A has a real part that is bigger than or equal to this quantity over here. Again, this pi of x comma u is the stationary distribution of this Markov chain, and the maximum value it can take is like is 1, and therefore you can show that if your discount factor gamma is bigger than half, the right hand side is bigger than or equal to minus half, and therefore therefore you can show that the asymptotic covariance is infinity if your discount factor is bigger than half. Okay, and that implies an asymptotic mean square error convergence rate that can be like much slower than 1 over n, and it's given by this quantity over here. Okay. Again, like I said, nobody uses step size of alpha n is 1 over n. So it's much more common to use a step size of this form. So here n of x comma u is number of times you have visited a particular state action pair x and u. I call this state action dependent step size. In this case, you can get rid of this pi matrix that used to appear in the previous linearization matrix. And this is what the linearization matrix looks like for this algorithm. And once again, the maximum eigenvalues of this matrix A can be precisely computed to be like minus of 1 minus gamma. And it corresponds to the right eigenvector all once. And in this case, once again, if you choose gamma to be bigger than half, then this lambda max of A is bigger than minus half, and therefore the asymptotic covariance is once again infinity. And once again, this implies an asymptotic mean square error convergence rate that is slower than 1 over n in this case. But if you scale up the step size by 1 minus gamma inverse, then you can guarantee a convergence rate of 1/n. Okay. But what that does is it also scales up your asymptotic covariance matrix by this factor 1 minus gamma to the minus 2, which I think is essentially the reason for all this such a term to appear in all these finite time bounds. So this 1 minus gamma to the minus 2 is essentially the reason for 1 minus gamma to the minus p that I showed in my first slide. Okay. So let's analyze, let's do a similar analysis for relative Q-learning algorithm. So this is the main contribution of this work. So let's look at the linearization matrix for relative Q-learning. It's essentially the same as the one for Q-learning algorithm, except that you're also adding a rank one matrix over here. And that can be like super helpful, and I'll show you how. So firstly, the eigenvalue that corresponds to the right eigenvector 1, which was earlier minus of 1 minus gamma, now it is minus of 1 minus gamma plus delta. Okay, and delta is a degree of freedom that you can choose, and you can always make sure that by choosing a delta large enough, you can make sure that this is very small. Okay. And all the other eigenvalues are have real parts that are strictly bounded away from minus of 1 minus gamma rho star. Here, rho star is a scalar that is defined over here. You can think of it as like sort of if your problem has a finite mixing time, then rho star is always smaller than 1. And even if the mixing rate rho is like equal to 1, you can show that rho star can be smaller than 1. So this is something that is problem dependent rho star. And if you choose a step size of this form, okay, earlier it was minus of 1 minus gamma inverse. Now if you choose a step size of this form, you can guarantee a finite asymptotic variance, and therefore the asymptotic variance will be proportional to this quantity over here instead of 1 minus gamma to the minus 2. So this may not look like a very big improvement, but the point here is no matter how big your discount factor is, gamma is, if your the problem that you're looking at has like finite mixing time, then this rho star is always strictly smaller than 1, and therefore like this is always bounded away from this is always like it's a finite quantity with respect to how gamma is closer to 1. Okay. And that can be like a big improvement, at least in many examples. Okay. So here's a basically a one slide summary of what relative Q-learning algorithm is essentially doing. So this basically summarizes all my previous slides. So here, P phi star is the transition probability matrix that corresponds to the optimal policy phi star. Okay. And there's one eigenvalue at 1, and all the other eigenvalues are have real parts that are strictly smaller than 1, but there are 2 more eigenvalues that have that are on the unit circle but have real parts smaller than 1. The eigenvalues of this matrix AQ, so AQ is the linearization matrix for the Q-learning algorithm, are essentially a scaled and shifted version of these eigenvalues over here. And you see that this lambda equal to 1 eigenvalue becomes a problematic eigenvalue for the linearization matrix. So remember, you want all the eigenvalues to be bounded, to be strictly smaller than minus half. The real part should be strictly smaller than minus half to have finite asymptotic variance. But there is one eigenvalue at minus of 1 minus gamma. And to get rid of this minus of 1 minus gamma eigenvalue, what you do is you multiply this by 1 minus gamma inverse, and that becomes minus 1. So that's the minimum scalar that you have to multiply this linearization matrix to get finite asymptotic variance. And what you're doing in this relative Q-learning algorithm is essentially you're taking this bad eigenvalue and then you're moving it somewhere inside. And it would be really cool if you could do that in general, but this becomes very easy in tabular Q-learning algorithm. And now the problematic are they're not so problematic anymore, but the most problematic eigenvalues are corresponding to the eigenvalues that have the second largest real parts that correspond to these 2 eigenvalues here. And these are always bounded away from the right half plane, no matter what discount factor gamma you choose. Okay. And hence the title uniformly bounded variance. Okay. So how does this perform? So here what I'm plotting is like, I'm plotting three different Q-learning algorithms. First is a Q-learning algorithm with optimal step size, that is 1/1 minus gamma, that is necessary for finite asymptotic variance and 1/n convergence rate. And I'm also plotting a Q-learning algorithm with the step size that is optimal for the relative Q-learning algorithm. And I'm also implementing the relative Q-learning algorithm. And what I'm plotting here is I'm choosing two different discount factors. They're pretty large, 0.999 and 0.9999. And when I implement the relative Q-learning algorithm, I complete the relative Q value function, and I showed that it has a direct mapping to the Q function, and then I get the Q function from that. And I'm plotting the maximal Bellman error for each of these three algorithms. Okay. And you see that for the discount factor is 0.999, the Q-learning algorithm with optimal step size, it does goes close to zero, but it's like very, very noisy. And if you make it discount factor even bigger, then it becomes even more noisy. But the relative Q-learning algorithm seems to be like sort of, have an unchanged behavior here. And if you don't choose the step size to be big enough, then you see that the Q-learning algorithm like takes forever to converge to zero. Um, and again, you should guess that this should be due to a constant, and that's what we kind of show next. So a small twist in the tail towards the end of the talk. I won't take long, but this is another result that we showed in the paper. So what we show is we just showed that the eigenvalue that corresponds to the right eigenvector 1 is minus of 1 minus gamma plus delta for relative Q-learning and minus of 1 minus gamma for Q-learning algorithm. So what we show is all the other eigenvalues of these two matrices are exactly the same. Okay, and if you choose any d-dimensional vectors v and w that are orthogonal to this all ones vector, then this v dagger sigma infinity theta w, where sigma infinity theta again recall as asymptotic variance, is the same for both Q-learning and relative Q-learning algorithms. And this is true only if you use the same step size for both the algorithms. Okay. So what this essentially means is that the convergence rate of the two algorithms is exactly the same, except in the subspace corresponding to the basis function. Okay, and this is true again only if you use the same step size for the both algorithms. Okay, if you pretend that if you want to use g equal to 1/1 minus gamma for the Q-learning algorithm and a different 1/1 minus gamma rho star for relative Q-learning algorithm, then this is not true hold anymore. Okay, and fair enough. So if you plot the span norm of the Q function estimate minus the optimal Q function Q star, this is what it looks like. The Q-learning algorithm with optimal step size is still bad, but the Q-learning algorithm with the step size that is optimal for relative Q-learning algorithm does almost exactly similar to the relative Q-learning algorithm when you look at the span norm. So and that I guess was like sort of a, in some sense surprising, but also in some sense kind of obvious result that we found. Okay, but does this property extend beyond tabular fitting? And I don't think so. Yeah, because I think there's a sort of a correlation between the parameters of constants and other basis functions. So in conclusion, we use asymptotic theory of stochastic approximation to design and analyze relative Q-learning algorithm. It seems to be that the most of the complexity in classical Q-learning seems to be spent on estimating this constant that you may not care about, because ultimately all you want is the policy. Keeping everything relative doesn't really hurt. The relative Q-learning algorithm results in asymptotic variance that is like uniformly bounded for all discount factors smaller than 1. It also gives us the Q function by just adding a constant, but I guess we don't really need it. And similar sort of analogy holds for 3D learning algorithms when used as a part of actor-critic or LSPI algorithms. And once again, the algorithm can be zapped, but the difference is the linearization matrix AH is much better condition for the relative Q-learning algorithm and than for the Q-learning algorithm. And you can also get a globally stable relative Q-learning algorithm similar to using techniques that Sean already mentioned. You can apply averaging, acceleration, variance reduction, all these techniques to even relative Q-learning algorithm, and the performance improvement will be the same. And the next question is like the open problem: can we get a finite time analysis? of relative Q-learning algorithm, and can we extend this theory to episodic reinforcement learning? And so here are a list of references, and thank you. Yeah.
Great. That's the old friend. He's doing fine. Don't worry.
Okay.
So I guess so. I don't see any questions in the. Let's see what time.
Yeah, it's time.
Yeah, I think it's time. Yeah, I think we'll just have defer questions till later, unless there's any quick ones. But I don't see anything.
I'll stop the share.
Yeah. Okay. Thank you very much.
I have a quick question.